Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
About how to make wireless local area networks faster and fairer. So the good news here is that access point-based 802.11 WLANs are becoming ubiquitous, and we see it everywhere. The bad news is that the spectrum is, as it stands, is used inefficiently and unfairly, especially in two occasions: when nodes transmit at different data rates, or when there are many nodes. So I'm going to give a little bit background. I'm sure probably most of you know what an AP-based WLAN is, just to make sure. Most of the work that I'm going to talk about, the results focuses on AP-based WLANs, but also applies to ad hoc networks. And in an AP-based WLAN, we have one AP and a bunch of clients, and all the clients each client associated with the particular AP, and then the access point schedules the frame transmission to the clients. Each node, both AP and clients, run a distributed medium access control protocol. Okay, that's just a AP-based WLAN. One thing is that the capacity, the channel capacity, right? The capacity of the networks depends on data rates. So this is the aggregate TCP throughput when two nodes are, sending TCP data. So in case when both nodes sends at 11 megabits per second, the aggregate throughput is about 5 megabits per second, right? The reason for that, you might ask, they are all sending at 11 megabits per second. Why 5 megabits per second? Because one, TCP had TCP-X, so TCP-X are overhead. And the other, 802.11 has physical layer framing overhead. In particular, this preambles has to be sent at either 1 megabit per second or 2 megabits per second. And that takes 20 or 25% overhead. So that's the reason, because of those overheads, even when all nodes are sending at 11 megabits per second, the aggregate throughput is 5 megabits per second. When two nodes are sending at 1 megabits per second, the aggregate throughput is about 0.8 megabits per second. Right? So the only things to get out of this graph is that channel capacity varies with data rate. Now you might ask, why would you ever want to send at a lower data rate? So there are two reasons for that. First reason is that we now know that there could be multiple standards, and new standards come with better modulation scheme, which means faster data rates. So 11G can run faster than 11B, right? So they have to coexist in the same spectrum. The second reason has to do with the channel conditions. Each modulation schemes are only good for a certain kind of channel conditions. And this is actually a achieved throughput of a single transmitter and a single receiver, as the distance between the two varies. Here, TCP throughputs are a little bit less than before because we run RTS-CTS. RTS-CTS basically is a packet exchange protocol to solve the hidden terminal problem, so it adds more overhead. And as you can see, if the distance between the receiver and sender is less than 100 meters, then you would always choose the fastest data rate, right? 11 megabits per second. Now, what happens is that if the distance is more than 100 meters, then sending at the next best data rate is more efficient. Yes? This is simulation with recent fading, but experiments also have similar graphs. Yeah. Sorry, should mention that. Yeah. Anyway, so that's the reason why we would see multiple data rates in the air. Okay? So now we look at it. So if nodes may be transmitting at different data rates, what will happen? So we look at the simple scenario where there are two nodes, N1 and N2, trying to transmit to a common receiver. Right? It could be the AP, it could be anything else. So first problem statement is that ideally we will want the medium access control protocol to take the responsibility of sharing the resource. So there is the shared resource. And assuming that all nodes have equal priorities, which is what the default option now, then the idea is to distribute among distribute the resource equally among entities. There are two questions to be raised. What is the resource? What is the shared resource? And what are the entities that are sharing the shared resource?
So you say that the resource must be distributed equally in all the entities. That doesn't necessarily have to be true, right?
Sure. So this is, like I said, assuming that if each entity has equal priority. I'll talk about how to do the QoS on top of that. In general, right, if your neighbor buy an SS point, you buy an SS point, you don't really want your neighbor to, have more capacity than you, right? Nobody wants going to pay the same amount of dollars for it. So that's what I'm talking about. But we will touch on QoS later. So we believe that current MAC protocols imply wrong answers to these two questions. Okay, this is the experimental graphs chart. Basically, I have two nodes running Cisco AeroNet cards. The way to read this graph is the bottom bar is the achieved throughput of node 1. Okay, I show you the little graph with two nodes transmitting, and the top bar is the achieved throughput of node N2. Okay, and when N1 is sending at 11 megabits per second, and when N2 is sending at 11 megabits per second. That's what the achieved throughput each will get. And the aggregate throughput is a little over 5 megabits per second, right? So
the nodes of the source of the TCP flow.
Yeah, that's right.
Sync is on the far side of that.
Sure. Yeah. Okay, so it makes sense. They achieve roughly 2.5 megabits per second each. Now, when they both transmit at 1 megabits per second, each node achieves 0.4 megabits per second. It's all expected. So the question is, what would happen if N1 transmits at 1 megabits per second and N2 transmits at 11 megabits per second? So I would say N1's throughput, because it's still transmitting at 1 megabits per second, it should still be 0.4. And N2's throughput should still be 2.5. That's what I would expect, wouldn't you? Okay, then the talk will be over. So anyway, the aggregate throughput, we would expect it should be around 2.9. That's not the case. What happened is that N1 actually miraculously get a little bit higher than it used to get. And N2 get the same little amount. Instead of getting 2.5, it got 0.7. What happened? Nothing has changed for me. I'm still 11 megabits per second guy. Somebody changed. My competitor changed its data rate, lower its data rate. Suddenly, I suffer. So I think that's a problem. So you can see the aggregate throughput is now very close to the 1 megabits per second capacity, right? So I would say the desirable alternate answer is that it doesn't matter what my competitor is. Whatever he's doing doesn't really matter. I'm the 1 megabits per second guy. I got 0.4 megabits per second, effectively 0.8 divided by 2. Yes? Yeah. Yeah. Because, these are all very low loss rate in this case. So, so then I've claimed that nodes throughput shouldn't really depend on other nodes' data rates, right? It should only depend on my situation. That's a desirable alternate answer. The reason that's not happening is because 802.11's MAC protocol says if there are n transmitter, each transmitter should get approximately equal amount of transmission opportunities. And in each transmission opportunity, you got to send one frame. So what happens is if the node is transmitting at a very low data rate, it says the same size frame, now it's going to occupy the channel a lot longer. So then you can imagine, this is the time, right? The amount of transmission time. You can imagine that basically the effective throughput is pretty much dominated by the slowest guy, right? The slow guy. So that's why I call it frame-based fairness. 802.11 thinks frames are the resource, or frame transmission opportunities, right? So it implies this notion, the resource is the frame transmission opportunities. And frame-based fairness, when all competing nodes use the same data rate, it means that the amount of channel time that it uses, right, each node uses is roughly equal. But then if you are competing, a slow node and a fast node competing against each other, the slower node is going to take the 84% of channel occupancy time. That's the amount of time that its data frames occupies in the air, right? And that's the reason why it's very close to the 1 megabits per second capacity. So we argue that fundamental shared resource is not frame transmission opportunity. It's the time, the channel occupancy time, to be exact. Time is what matters, and we claim that each entity should achieve equal amount of time. Yes?
Simply, was this role not part of the standard was defined?
Excellent question. So I wasn't involved in defining standards, so I don't exactly know the exact answer. But I will guess that at the beginning, when we come up with the wavelength card, right, there are basically, 1 or 2 data rate, no more than that. So, if you send control packets at 1 megabits per second and all data frames at 2 megabits per second, this problem just doesn't exist. So, that's, plus frames are easy to achieve, time is not. For those 2 reasons. Now you can see a lot of diverse data rates in the air, and this beginning to become a very big problem. So each entity should get the same amount of transmission time, independent of data rate, independent of frame size. It doesn't matter. So that automatically implies that if you are the fast guy, you will get to transmit more frames than the slow guy. So this was published in Usenix. Now, so I call it time-based fairness, and TF denotes for time-based fairness. It doesn't favor slower nodes. If you look at the channel occupancy time graph, right, this one is frame-based fairness, this is time-based fairness. Well, so the frame-based fairness graph are all experimental, right? Time-based fairness, I'm sort of envisioning an ideal MAC protocol. If you can achieve time-based fairness, that's what channel occupancy time should look like, which is 50-50 all the time, regardless of whatever data rate you're using. As a result of that, frame-based fairness and time-based fairness are identical in terms of throughput when every node uses the same data rate. Now, when one guy uses a slower data rate and the other uses a faster data rate, they differ. This little small bar is exactly that little small bar down there, which means it's only dependent on your data rate and the number of competing nodes, right? So it improves aggregate throughput. Another way to look at it is that from the 1 megabits per second guy, he's going to lose about 35, 38% of the achieved throughput. But you're thinking about the faster guy gaining about 240%. So as a result, the aggregate throughput improves. All right. Now, hopefully, I'll convince you that time is the right thing to do. It's the shared resource that we should think about. What are the entities? How should we think about entities? So we look at this example. In this case, there's one access point, and there are 4 clients, right? A1 through A4. And here's a scenario which is actually very practical. It happens all the time. Is that access point has 3 downlink flows, 1 to each of the A1, A2, and A3, and 1 uplink flow going from A4 to AP1. They're all trying to send as much as possible. So what would happen is that in 802.11, each transmitter contains in the same manner. So access point is one transmitter. Uplink client is another transmitter. So you basically have 2 transmitters. And for each frame that AP1 transmits, A4 gets to transmit. So by the time AP1 finished transmitting 3 downlink frames, 1 to each A1, A2, and A3, A4 would have finished transmitting 3 frames. So I don't think that's fair. The transmission opportunities for all downlink clients is equivalent to transmission opportunities for each uplink client, right? So that's why some companies running, trying to put 802.11 video or audio, and they say, hey, access point saturate is much faster. That's the reason. So then they start saying you can only support 5 or 6 flow if you have 1 uplink flow. Okay. So, these are the reasons behind those comments. And the number of entity is 2 because there are only 2 transmitters. And we think that's wrong. It should be links. We should even though it's a wireless channel, we should be able to abstract out this link notion, which is that in this case, there are 4 links, right? AP1 to A1, that's a link. Same link as A4 to AP1. And we claim that each link should receive the same equal amount of resource, which is channel time. Yes?
That depends upon whether the AP and support, if you allocate a resource of 25, 25, 25, 25, then the AP should be able to support calculating 0.75.
Sure.
If that is not the case, then you take that into account.
What is it, the example that that's not the case?
So, for example, let's say that the AP, because it becomes CPU box,
Okay.
it cannot support, you
Oh.
have 1 megabit per second, like it can't concept 0.25 megabit per
Sure,
second
sure.
data.
Exactly. So that's sort of, you're talking about sort of maximum allocation. Sure. The MAC protocol that I'm going to talk about that later will achieve maximum allocation, which is that if there's, he's asking whether if there's a node that cannot really saturate the channel, cannot use up the capacity you allocated to it, is it going to go wasted? The answer is no. That's a bad thing. Exactly. Very good question. And what we want to do is, given the fact that if you can use up as much capacity as possible, we want to be fair. Okay, so now the number of entity is 4, right, instead of 2. Yes? What are the semantics of broadcast or multicast traffic? So I haven't really thought much about multicast yet. So it depends on what you want to identify as a link. Here I'm identifying this as a unicast link. I mean, if you think that each multicast, group should also be considered as a link, that can be worked too. Later on, when I show the MAC protocol, what it is that it's effectively all it matters is you define link notion, and then you run basically each instance of MAC as a link. Even in one node, there could be multiple instances of this MAC running, and that will scale out well. Yeah. So now each link gets the same amount of channel time. So for each frame that AP1 is transmitting to each of the downlink clients, A4 only gets to, each link gets to only transmit 1 frame. Okay. So just to summarize, probably 802.11 is thinks that the shared resource are frames, and the entities that are sharing the shared resource are nodes, rather transmitting nodes. And then our proposal is time-based. Channel occupancy time is the shared resource, and entities are the links, not the node. So time-based per link fairness is efficient and fair, and those are just summary of what I said before. Okay, so I won't bore you with this by repeating. Now let's switch a little bit gears. Okay, time-based per link fairness is good. What do we do? So how do we achieve it? One thing is we developed 2 solutions. One is centralized, and second is the distributed. So this centralized solution actually was published in Usenix 04. So there's a centralized scheduler, and we're going to make it compatible with 802.11. So just let the 802.11 MAC protocol run, and we're just going to modify a little bit of code inside the driver, basically the scheduler. And it works if you have one single AP and there's no nearby AP share the same channel, then it works. It also works maybe in case of Microsoft where everything falls in single administrated domain, and even if you have multiple APs nearby sharing the channel, you can coordinate and compute the fair share in a coordinated fashion. In that case, then it works. The way it works is that it's basically shapes the downlink traffic to clients. That's all it is. It doesn't care whatever the traffic is, but it's going to regulate the traffic flow coming from the AP to clients because everything goes through the AP. Right? That's what it's going to do, and the way it does it that it's actually going to monitor the channel time usage in both uplink and downlink direction, right? So for each client, the AP monitors the channel time usage because it knows when it either transmits or receives a frame how long it took. And based on this, it also knows how many number of competing nodes out there it can compute the fair share, right? Based on this, it's going to regulate the downlink flow to the client. Basically, I'm not going to transmit to you unless you have enough credits. So this works without whatever I said works, so long as you have at the transport layer that you have feedback-based congestion control protocol. For instance, TCP, RTP are great example. Any kind of that, the idea is that whenever for a transport layer data frame, there's an ACK coming back in another direction. So access point always have a flow that it can regulate going back to the clients, either that be a TCP data packets or TCP ACK packets. And by throttling that packets, it will also limit the amount of data that client can send. Now, if the client is just a UDP flow and trying to send 1 megabits per second at will, there's nothing much you can do about it. So you can drop packets all day long you want, but it would have already used the capacity as it wants, or whatever allowed by 802.11. To solve that problem, the only way you can do is you then need a little bit overhead. You then have another protocol running saying that UDP client, you need to slow down. Yes? Both rate limits and drops, yeah. You have a queue, you try to rate limit. If the queue overflows, you drop, yeah. Okay, so I'm not going to talk more about it. It's actually, I hacked the Linux host AP driver, implemented this thing. It works. So this is the experimental results. So we have, in any case, it's all 802.11. We didn't change the MAC. We can't change it anyway. We didn't change the MAC. And the bar on the left side is basically without TBR, and the bar on the right side is with TBR. So we modify the access point, and as you can see, the aggregate throughput improves as expected. Okay, sorry. Okay.
I'm just curious. I was thinking about the UDP client standard problem. One potential thing, and this one we have is here, modifying the whole AP software. We simply hold back on the MAC level acknowledgement. The AP one cannot acknowledge the UDP.
Excellent idea. The problem is the ACK is actually used for dual purpose, you see. With 802.11, the ACK is not just for reliability, right? So you can actually do it. Then the problem is you also need to react to because then the clients will be just backing off and stuff like that. So you need to understand how this is going to affect the back-off algorithm. Yeah. And if you can somehow adjust it and make sure that it reacts appropriately, I think that's certainly one way to do it. But the other problem is that the node also needs to know that you are holding the ACK and not really, it doesn't retransmit. What happens if it retransmits, then you waste capacity. So it's not an easy problem. So I think this all comes down to the point that the ACK is serving dual purpose. And actually, one of the things that I'll talk at the end is, as you see the distributed MAC that I suggest, then you would, basically there's a nice decoupling of congestion control in the network versus reliability. Yes? Yes. Everything in the air. Yes. You doesn't matter. So whatever data, you're counting the channel occupancy time of the data frame. And there are hooks in the firmware that you can know how long it takes, right? For each frame you're counting, you're not counting. You're looking at the TCP packet. This is purely at the link layer. So you can consider as a logical link layer protocol. It's above MAC, but it's certainly below IP. Yes. Yes, I certainly have that. Yeah, they are comparable. For equilibria clients, they are the same as they used to be. Yes. Yeah, it wasn't on that. Sorry. I mean, I have a tons of graph. I just picked the interesting one. Yeah, I mean, it's a good question. But actually, it's also in the paper. You can look at the uses. Yes, Victor.
So, how many years ago, there was talk about fairness. There was a definition of fairness which took into account application and errors. So if you were, for example, lagging, so you would not be able to send read. So is that incorporated or not incorporated? You don't care about that kind of fairness?
This cares about it. The centralized thing cares about it. So it doesn't really matter whether you are, how many errors that you are you are suffering. But the thing is, I need to know what, so the retransmissions are a hard thing because you don't know who transmits, right? Who do you account for? Usually now, if I don't know who's transmitting, then I just think that it's somebody transmit and equally divide. So once you know that, then it's sort of getting incorporated in this, right? In a sense that I'm keeping track of all the frames that you are transmitting, right? So all the retransmission has been computed, and roughly you should be able to get the same amount of time, even though you are suffering more errors. And our distributed protocol certainly deals with it, because distributed protocol actually has more information, because it has the information because it knows what it transmits. And I'll talk about that. Yeah. That's
the other question which you might also address later is PCF tries to do something similar. Except, you could implement something on the notion of airtime fairness and put it in a non-cooperative function as well, right?
sure.
But that didn't go anywhere,
Right. Well, PCF has a lot of problems, right? So and it's complicated, and this is basically it's not PCF, it's still DCF, but you do some ad hoc solution. I mean, some engineering solution to fix it. I'm not necessarily saying that this is the only way to fix it. Yes, if I have the chance to redesign the Mac, which I will talk about, then I will throw away 802.11 and redesign. Okay. So now this solution as a centralized scheduler is fun, but it doesn't work if you and your neighbor are running APs nearby. And the other 2 weeks ago, before I came down out west, then I turned on my laptop and looked at it. There were 12 access points within radio range from my room, and you mean that's a lot of competition. And there are only 3 orthogonal channels. You can imagine there are a lot of overlaps exist. So you compete with multiple access points nearby and multiple clients nearby. There's really no coordinations going on. I can't just say, hey, here's a wire run through your AP and my AP, and we coordinate and we got better throughput. That doesn't work. They're not going to do it. So now you want to distribute the solutions. And maybe for friends it might work, but you want to distribute a solution, right? So now, following up on what Victor asked, okay, why don't we think about better solution? Okay, while we are at this, why don't we redesign distributed MAC protocol? Oh, one thing I want to tell you is also PCF is centralized, right? The thing with PCF is also what happens when you have multiple PCF coordinators nearby. You somehow need to resolve that distributedly. So I assume there's no assumption of coordination here. The only coordination is that everybody runs the same distributed algorithm that I'm going to describe. There are 3 challenges. One is to achieve per link maximum time allocation. I don't know your name, but you mentioned that before. If a node cannot use the capacity, then that capacity should be able to redistribute among other nodes, right? So the goal is channel utilization is always 100% if there is enough load. Beyond that, you achieve per link time allocation, okay? Then you do another thing with 802.11 that we're going to see is that it doesn't scale well if the number of transmitter increases. And also, finally, you want to achieve efficient equilibriums, and I'm going to talk about that in the next 2 slides. And our solution is, I call it FAST, Fair and Scalable Time-based MAC Protocol. Okay? The challenge 1, achieving maximum time allocation. Why is it hard? It's hard because the number of links could be varying all the time. And the other thing is, more importantly, the load varies. Not all links are trying to saturate the channel, right? Some are sending at audio flow 8 kilobits per second. So the idea is that each link I will achieve at least its load if it's less than its fair share, right? Otherwise, then it will get at least its fair share. Okay? All right, that's challenge 1. And 802.11 doesn't achieve maximum time allocation, right? I have to say that. Challenge 2 is achieving desirable equilibria. So before, we were all in a very nice environment where we think that every node is sort of cooperating each other. But the MAC layer these days now expose a lot of APIs for vendors to optimize. Right. In this particular case, we can imagine every vendor can implement its own rate adjusting protocol, auto rate protocol as you would. And basically trying to find, the goal is that each device will try to maximize its own achieved throughput. right? Using the interface, whatever exposed by the MAC layer, in this case, you can set the data rate, you can set the frame size, and all that stuff. So we need to worry about when each vendor tries to do that, or each user tries to do that. Is there going to be a situation that you will try to do it so that you achieve higher throughput for yourself, but the overall aggregate throughput becomes significantly lower? And there is such a situation. I showed that by simulation, and I also showed that by game theoretical analysis, and I proved that this situation, effectively, it leads to a Nash equilibrium which is not efficient and not desirable, where some nodes just basically lower the data rate intentionally, even though they shouldn't, just to get higher channel time share and improves a little bit of loss rate. The idea, what I'm trying to say is that with time-based fairness, what's going to happen is that it's going to have the guarantees that each competing node, right, if they have enough load, they will always get 1 over n timeshare. Now, if I say that to you, to each node, that you're going to get the fundamental share resource no matter whatever you do, what would you do? Then you will go back and look at the graph that I showed earlier. Based on the loss rate, you will always pick the most efficient data rates to maximize the throughput. That doesn't happen in 802.11. That will happen if we give timeshare guarantees. Okay? So you can, these papers are available online. I'm not going to talk more about that. Now, finally, cool things is that, yeah, this graph is probably misleading. I should have started from 0. But anyway, so it's, here is the number of nodes, number of transmitters is increasing, right? And then the aggregate throughput just drops in 802.11. So what happens? Well, here is the reason why. If you look at the collision rate, it's actually increasing. Right? So all the way from 3% to all the way up to 30% as the number of nodes increases. That's the reason why the aggregate throughput decreases. So 802.11 doesn't scale very well with the large number of nodes. And it's not, I mean, you know, when it started, nobody really thinks that 802, you will use more than 1 or 2 nodes, and that was fine, right? DCF was 802.11 MAC was a very robust mechanism for that, yes. With what? This one. Without RDS CTS.
So what RDS CTS all about? Because
No.
package that collide would be this small package.
To a certain extent, that's true. But then, would you willing to pay 20% overhead for RTS CTS? I mean, right?
That is the far end we are paying around 30%.
Right. But even if you pay RTS CTS 20%, when your collision penalty reduces. What he's saying is that this graph, so collision rate doesn't change. Agree? So the throughput, what he's suggesting is that throughput may not be as drastic if you use smaller packets to collide, and he's right. I mean, it's a function of the penalty of collision, and also the overhead. I mean, you can't just use RTS CTS. If you use RTS CTS all the time, then automatically you pay 20% penalty. So what is fast? Fast, actually, the property of fast is achieves per link maximum time allocation, achieves desirable equilibria, and it achieves scalability. And I can't talk the other two. I don't have enough time to talk about the other two, and I will just talk about scalability. So before we jump into the technical details, just a little bit background on the carrier sense multiple access MAC protocol. That's what 802.11 does, and any kind of CSMA variant slotted system, you can imagine it will do something close to that. The idea is that if you have a frame to transmit, you do a carrier sensing. And first you pick a counter between 0 and CW, it's contention window size. So between 0 and CW, and then you sense the carrier. At the end of each slot, and you see no carrier, that means your slot is idle, then you decrease your counter. Now, as soon as you hear in the middle of the slot or in the beginning, whatever, at the end of each slot, you know that there's a carrier presence, then you actually pause the counter, okay? As soon as the counter reaches 0 at the end of the slot, you don't need to do anything, you just transmit, okay? Now, if the frame is received successfully, by the receiver, then it will, within 10 microseconds, it's going to send a acknowledgement packet. Okay, and as soon as the sender receives the acknowledgement packet, it resets its contention window size to CW min, which is 31 for 802.11b. If no synchronous acknowledgement is received by the sender now doubles the contention window size. Right? So the idea here is that if I don't get if a frame is lost, right? If you don't receive an ACK, then a frame is lost. Then it's probably most likely that there might be a lot of nodes trying to contend for the channel, and we should back off, right? So that collision is not too high. So that's exponential back off. The key thing here is that 802.11 implicitly assumes that a loss is due to collision, right? But a loss could be due to random channel errors, in which case then backing off wouldn't help. Some errors are helpful when you back off, but some errors are not. So there's no assumption there. I mean, so it just assumes that a loss is due to collision and it'll back off, okay? So now what I want to go over is sort of an example here and show how it operates. Basically, two nodes A and B, and they're both trying to transmit. And at the beginning of time, A flips a coin and pick number 5. B flips a coin and pick number 8. So at the end of the first idle slot, A has decremented to its counter to be 4, and B has decremented its counter to be 7. Is that clear? Okay. Now clearly A is going to reach 0 first, and then it transmits, right? The green packet is the A transmission. And usually this green packet is maybe about 50 or 60 times bigger than each idle slot. Depends on the rate you're using in the MAC protocol. So then B, it hears the busy tone. And what B has to do is actually B will decode the header. If it successfully decodes the header, it will have a bunch of information. And anyway, it knows how long the successful transmission takes because it keeps sensing busy and it will freeze the counter, right? Now, once it gets here, successful transmission, then node A actually flips another coin. Unfortunately, it picks the number 3, which is what the remaining number of node B. Now they collide at some point, right? So when they collide, B still doesn't know how long the collision lasted. B doesn't know whether it's the packet is lost. It doesn't receive a synchronous ACK, so it knows it's lost. But it doesn't know whether it's lost due to channel errors or collision. But what it knows is how long it took, right? So those are the key pieces of information. And the third information is that if you have a data all the time and you're sensing the carrier, right? You're doing this CSMA stuff. You know what's the idle time between any busy events. Right, so exactly, perfect. So you are thinking of, for instance, what's that? How long it's in the transmission lasted. If it's transmitted, it knows when it ends, right? From the beginning, it transmitted, it knows which data rate it's using, it knows the time it takes, right? If the two frames collide and they are not identical length, right? What happens is that the smaller frame, as soon as it finishes, its ACK timeout is expired, it needs to back off again. Then it will sense the carrier. Then it knows it's busy. So it can treat this whole thing as busy event, starting from when it transmits until the end of the other guy. So you see what I'm saying by how long it lasted. So each event, if you can hear it, you know how long it lasted. So those are the key pieces of information. Again, for successful transmission, you know the source and destination. So those we're going to use a link identifier, right? That's why we're doing in node pairs with the direction. And these key pieces of information are currently available to all the CSMA MAC, but not really used by 802.11. If it's successful, you will decode the MAC header because you need to know whether it's the whether it's directed to you, right? That's when you know whether it's intended for you. Everybody will decode the MAC header. If you can't decode the MAC header, it's a failed transmission. Yeah. Excellent. So you're talking about hidden nodes. So if you have some hidden nodes, then some nodes may not be able to hear successful transmission. And so then if there's hidden node, then you got to do something about it because collision rate is going to be much higher than what I usually show. And if you run RTS, CTS, then every node within 2 hop radius will know how many, what's the incoming, the next transmission. Right. Okay, go ahead. Sorry, I mean, it's just an example. In this case, then you start with 0 to 31. That's the default for 802.11, but that's not the default for our protocol. But right. So then the higher the number of nodes, you want to increase that. That's the reason why we have the exponential backoff. So you keep doubling the CW. So CW gets bigger and bigger. Hopefully that scale, and it doesn't scale that I show you. So in fast is a round-based CSMA MAC. You basically say, okay, we don't use the exponential backoff scheme. We're just going to adjust our own contention window size. And we do that not for each frame, rather for each round, and using the information available to us. And I'm going to define, of course, what each round is. Then concretely, we can pose the problem as follows. We want to set the contention window size such that the observed collision rate, PCOL, the observed collision rate is PCOL, which is a configurable system-wide parameter, irrespective of load. Okay, that's a key thing. So you will ask, why shouldn't PCOL be very small? And I'm going to answer that in the next slide. So the idea is that we want, regardless of the number of nodes or the load, we want to always achieve a certain collision rate, always. Okay? A positive collision rate. That's the key. So instead of 802.11 going this way, we want a flat collision rate. That's the goal. Now, to achieve that goal, we use two-step process. One, in each round, we're going to be estimating the number of contending links. So the number of contending links is different from the number of active links. Because you can have nodes that transmit one frame every so often, right? Every second or something. Then you have nodes that's transmitting all the time. And if you have 2 nodes like that, that doesn't mean the number of contending links is 2. The number of contending links probably is just 1.1. So this is a very hard thing to do. But we're going to try to estimate it. We're going to estimate it. And then the way we estimate is that NC is going to be the number of contending links in a round. And then we're going to adjust the round size. We change the problem to adjusting the round size until we know for sure that the number of contending links in a round, that is the number of successful links in a round, is exactly the number of contending links. I'm going to go in detail on each of this step. If you don't get it, that's fine, because we go through each slide, and I'll try to explain it. Just an outline. So basically, 2 steps, we're going to estimate NC. And the second, if we know NC, and we have a PCOL, using that, we compute CW. That's it. So the next steps, actually 3 steps now, because we need to know what PCOL should be, and then how to compute. Then I flip the thing. Assuming that we know NC, some oracle give it to us. What is the CW supposed to be, so that we achieve the sustained constant collision rate? And then how to estimate NC. PCOL is a configuration parameter, system-wide configuration parameter. The problem is that you really don't want a very low PCOL, close to 0. Then the way we do the back off, you will necessarily have to waste a lot of idle time to reduce collision. And idle time are not free. They are overheads, right? In a perfect system, you will want no idle time and no collision. But in a distributed system, you need to pay a little bit of overhead for idle time. And so there's a trade-off between idle time and collision rate. And this trade-off can be pre-computed. It depends on what the average size of transmission, which is the collision penalty, and what is the size of each slot. For 802.11b, I believe what is the number? The number is like 6 or 7%. Okay. So that's also, you can imagine that as sort of an overhead that you pay. Now, we now do an analysis on how to compute the contention window size if we know NC. And PCall, we know it because we're going to set it before we ship the maps. So this is just two-node analysis, and TIFF has an approximation analysis. It's pretty cool, and I like it. I built on his analysis and do more generalized analysis. But here, so the idea is that there are two nodes trying to transmit. As far as node B is concerned, right? What node B sees is that every once in a while, node A transmits. It could be a failure, whatever. It knows that somebody is transmitting every once in a while, right? And what is that every once in a while? Every once in a while is effectively the average contention window size of node A, right? From B's perspective, that's what B sees, right? So I actually collapse the, each transmission to be just one either slot, one busy slot, right? That's okay. Now, the probability of collision from B's point of view is 1 over CWA average plus 1 because B has B also draws its number from uniform distribution. That means for every slot, B has an equal probability of transmitting. So that's what it is. Okay? So now you can generalize this to the number of contending nodes. It doesn't have to be a whole number, it could be a fraction. Roughly, that's why it's applied. And we can compute the probability of success based on this. And this is the observed success rate, right? And then we flip it around and said that if we set the contention window size to a function of probability of success and the number of contending links, then the actual collision rate is going to be exactly what we set. All we need to know is NC, right? That's the hard thing. If we know the number of contending links, we can set CW such that collision rate is flat, regardless of NC. That's what I'm talking about, right?
Because the average collision window is not a free parameter like this, right? Because it is, if you have a collision, then the following slot is actually double. You know that.
No.
It's not independent, right?
That's why I'm saying we don't double the windows now. We don't care. Exponential contention window size doesn't apply. That's right. Exactly right. So this doesn't apply for 802.11. You're right. Okay. So I have an analysis on that. And actually, I rewrote. I'm sure most of you probably. Yes, that's right. Yeah, that's right. Because I know that pretty well, I guess. And it's cool, I mean. It has some advantage. So I rewrote the CW average. And this equation, if you just focus on this, it just means that, right, it depends on the probability of success, which is what you input. And you just need to grow contention window size linearly with the number of contending links. Okay, excellent. Okay, now, you guys are going to ask me, how do you estimate NC? You said it's a hard problem. Okay, how do we estimate NC? So we're going to talk about that, and that's going to be the last piece of the talk. Well, after that, we look at the experiment. So we're going to say that NC is actually the average number of successfully transmitted links per round. Okay, that's what we're going to say. So round is a shorter time scale. In a shorter time scale, we just say, we keep track of this moving average, and we say number of contender is this number. Now, yeah, I'm going to define it. So we don't know. So now I just move this problem, right? Okay, trying to be smart and just create another problem. Victor asked, what is a round? That's the key, right? If the round is too large, what happens is that, let's say if I have 100 nodes that are transmitting frames every second, and I have one node transmitting frames all the time. If a round is large, I will see all 101 nodes. And then CW would be so large, the collision rate will be so low, then I waste a lot of idle time. So it's a similar problem, but this is a different unsolved problem, although the impacts are similar. So the round, if it's too small, then I collide too often, right? I collide too often. So what is the size of the round? Do you have a question? Okay, sorry. So the round is basically amount of time. So some number, so some milliseconds. So at the end of, let's say, 12 milliseconds, each node compute CW. And we're trying to figure out whether it is 12 milliseconds or it is 20 milliseconds or 100 milliseconds.
Everybody has to agree on this round number.
No, it doesn't. So in general, if everybody runs this algorithm, and it will converge to the same round, yeah, roughly.
No, the duration of the round.
No, the duration of a round is an independent parameter. Well, it's a parameter that each node sets. There's no static number. Because, as I said, when the load is changing, the number of contender is changing, the round needs to be adjusted. So I'm going to show you how to adjust the round based on whatever you see. And if everybody can here observe the same traffic condition, which is what they would be, then everybody will estimate approximately the same round size. Does that answer your question? Okay. Yes. Oh, this is only the scalability part, not the fairness part. The only thing that's similar with 802.11 is that, yes, I mean, it does the carrier sense. But the CW adjustment part of 802.11 is what affects the capacity allocation as well as the efficiency, right? So instead of 802.11, we're saying we compute CW very intelligently. 802.11 just double the window size whenever there's a loss. There's not much intelligence to it, right? It's a very simple and robust scheme. Yes, but within the framework of CSMA, 802.11 like CSMA, that's what we're doing. Is that the question? Yes. Excellent. I mean, you can look at it that way, yeah. Yes. That's right. That's right. You're right. You're absolutely right. So other extra things that we do, probably 802.11 nodes doesn't do right now, but they have the information is that when you compute the CW, you use other inputs. That's available to CSMA MAC, which is 802.11 doesn't do. Yeah, but you're exactly right. We have a, yeah, sorry, go ahead.
So the framework for doing this does not exist, right? WLAN allows you to change CW quite regularly, right? So I mean, how you change it is something you can add.
That's right.
But in terms of framework, I mean, still you got like compatible. Right?
Could be, yeah. That's right. That's right. Okay. All right. I'm going to talk about a wrong approach. Probably it's going to bore you. Maybe, I don't know. Maybe if you guys want to explain others, otherwise, if it's going to confuse, then I just put this slide, maybe you will appreciate the next slide a little bit more. But it doesn't really matter. So let's just go to the right approach. Who cares about the wrong one? Okay. What's the right approach? The right approach is that we're going to observe the average idle time between transmission events. And I explained to you that we know that number. We can't observe it. So, so idle average, that's the key thing that we're interested in. It turns out that this idle average number, the observed idle average, is roughly constant for any value of NC if a MAC is doing exactly what we are doing. If you set the contention window size such that you're going to achieve a sustained collision rate using this formula, then your idle average becomes to be roughly constant for any NC. And we can pre-compute this number. And because it only depends on the whatever we input, P-call. So we have a P-call that we want, let's say 7%. Then we compute the idle average. We know it. All we need to do is each node now try to achieve that. If every node tries to achieve that, the observed collision rate is going to be constant. And because idle time between transmission is constant, what you get is flat throughput. regardless of number of contenders, you're going to achieve sustained throughput. Okay? So the goal is that in each round, you know what the desired p-call and you know what the desired idle average is. And you will increase the round size if idle average is low. So you look at the idle time and you think, oh, average time we're seeing is actually quite low. Then we need to increase it. So then more nodes can be observed and can be used in computing NC, right? And then, so then CW will expand because there are more nodes involved, and idle will increase. So you keep adjusting the round size. When do you know to stop? You know that when the idle time is actually reaches that desirable time that you pre-computed, then you know that for sure you have achieved a desired collision rate. Okay? It doesn't use any feedback, any lost feedback. That's all there is. Okay, so I can talk more about this, how I developed this. Anyway, so I just want to show you that I'm not, just saying something, but analytically it's true. That's what the equation is. It only depends on the probability of success, which is what you input, and the number of contenders, but it's roughly, it's basically constant. And here's the graph. So in this case, then, this is individual collision events. So p-call over 2 is about 5.5%. So you input the system to achieve about 94.5 success transmission events, right? Then what you can see is this idle average is pretty flat. So if you set the idle average to be 5, that's what we should strive for, then you will achieve the collision rate of around 5.5% or 11%, depends on how you look at it, right? Individual collision rate is 11%, but each collision involves roughly 2 frames, right? So the number of collision events, probability of collision events is p-call over 2. Yes? No. There's no traffic model involved. I'm just assuming that whoever is sending and trying to saturate, it doesn't matter if it's 120 nodes and 100 nodes are sending at 1 packets per second. So long as the way they contend, right, and that transmission events are spaced out equally, average to a desirable number, the collision cannot be bigger than this. Collision will not be bigger than this. Yes? Oh, sorry. So for this is everybody is saturated. But I have run graph with, so what I'm trying to say is like if you have 10 nodes, right, and 5 nodes are transmitting at 100 kilobits per second, the other 5 nodes are saturating the channel, it would still be able to achieve the observed collision rate. Right. Yes. Mm-hmm. That's excellent question. So, all right, go ahead. That's right. Sure. Excellent. So, okay. So I understand it's great points. So actually, I would argue that 802.11 actually is not, it doesn't react like you were expecting. The reason is the following. If you have a lot of number of nodes, you react to collision. Problem is, as soon as you got to transmit one frame, you reset it to 31. Now you lost all the information. At every given point, a lot of nodes have no information on exactly what CW should be. So I claim that if it's transient, 802.11 could even have more problems. Now, having said that, I haven't run a lot of experiments with variable traffic. I've run some. That's why I'm saying that some nodes running at 100 kilobits per second, and the graph looks fine to me. But also, I haven't done a lot of analysis on that. So what I'm trying to say is that even regardless of transient or long-term changes in the number of nodes, 802.11 just doesn't converge very well. I mean, you can see a lot of other work where people are trying to do multiplicative, increase and multiplicative decrease that are much better than 802.11 or go, push, reset. Go, push, reset. I mean, you just don't get it. Even the average size is so far off. That's the reason why you keep increasing the collision rate. That's not the way that when CSMAs were envisioned, P persistent. I mean, but it's the way 802.11 does exponential backoff. Now, but I think that your question of how fast you converge is certainly an interesting one. And I have to say that I haven't explored much to it, but I have explored some aspect of it. Yeah. Okay, so a bunch of experiments. I don't expect you to read the slide that much. But anyway, so I run a bunch, and I'm going to show just selective graphs. So here's one scenario where we have 4 nodes, A1 and A2. And what's that? Really?
So it sounds like you already had a plan for how you would install that.
Yeah. Oops. That's right. Yeah. So usually, when I prepare my talk, and I have like 30 slides, and I show all 11E complication and all that stuff, my advisor said, "What are you showing? I don't even know what it is." So from 30 slides, now we have like 4 slides. But anyway. But yeah, I mean, I can talk about it on one-on-one if you guys want. There are cool stuff. Okay, so A1, A2, A3, A4. There are 4 clients, and half the nodes going to transmit at 1 megabits per second, half the nodes going to transmit and receive at 11 megabits per second, right? So in this case, as expected, if you use frame-based fairness like 802.11, the aggregate throughput is much less. Otherwise, fast, improves by 150%, right? No. Oh, this one is simulation. You're correct. Yeah. But the TBR is the experimental, right? Yeah, this one is simulation. So when I think last things that I needed to do, which I want to do is basically, hopefully, I can implement this. The problem with implementing is that the backup algorithm is in the firmware. So this is a huge problem. So I think that we have been playing with a lot of hardware. I believe that Ethros may do some tricks in terms of they kind of have these hooks where we can turn off the firmware backoff, and I will do the backoff in the software. It'll take some performance hits, and we see how Linux timers behave. I know they're not very, but we might be able to use some hardware interrupts. I haven't figured it out yet, but that's part of the deal. When I go back home and figure that out. If I get it, that's great. If I don't get it, I think I should still be able to graduate. Right. So another thing is one AP with, okay, so change the scenario a little bit. So one access point with 4 clients, and there's 1 uplink client and 3 downlink clients, right? They're all sending at the same data rate. And I just want you to focus on this metric here. So what it is measuring is the ratio of the maximum amount of time each client achieves divided by the minimum amount of time any client achieves, right? So clearly, 1 uplink flow is basically getting the combined capacity of 3 downlink flow, right? So that's the reason the ratio is roughly 3 for 802.11. But with fast, the ratio is 1.04. That means every link is within 4%. 3 or 4%. And actually it also improves the throughput. In this case, then there's no time-based or frame-based fairness going on, but it's just all the same, same size frame, same data rate, but it still improves throughput, but because we are optimizing the right idle time and the right collision rate. Okay, here's another situation where, the fundamental reason why 802.11, I mean, nobody can distinguish, well, I shouldn't say nobody, but we sort of agree that it's very hard to distinguish between losses due to collisions and losses due to channel error. And 802.11 does a reasonable job of estimating that by backing off whenever there's a loss. So what happens if you only have a single node and trying to transmit, you incur 10% frame loss rate, which is not uncommon at the MAC layer. I'm not talking at the TCP layer. TCP layer will be 0% because you do retransmission. And it just keeps backing off and you waste a lot of idle time. So fast doesn't do that. As long as it sees the right idle amount, it knows that collision rate is fine. So it doesn't care. It never backs off. I mean, so long as it doesn't need to. So, okay. And finally, the scalability. The number of contenders, this again is using, each node trying to saturate the channel. And UDP throughput improved by 26% as the number of nodes increases. But the cool thing is it's flat, right? Throughput is flat. So we're not talking about 802.11. This Mac can run in, WiMAX or whatever. If you want to have mesh networks with 10,000 nodes and you got a sustained throughput, that would be a cool thing, or 1,000 nodes. So I think we have, created this new variant of CSMA MAC protocol, which I would like to call it time-fair carrier sense multiple access with bounded idle time and with bounded collision. All right, excellent questions. Yes, I did. So I didn't have the slides yet. So what would happen is that fast is, in some sense, is less aggressive than 802.11, right? As you may. Because 802.11, the reason is because it's so aggressive that you have a very high collision rate. Now, you have 2 or 3 fast nodes running, right? And then you drop DCF, right? Then, if he is going to saturate the channel, what's going to happen is it's very likely that DCF node will actually gain a little bit more channel time than the other 3 nodes. Whereas the other 3 nodes will exactly get equal channel time share, but DCF will gain a little bit more than each of the nodes. Now, having said that, okay, so there are 2 ways to solve that, right? One is that if you ship fast nodes, right? Fast somehow got adopted and you ship fast node. One way is that as soon as you hear there's another DCF node, old node, then you resort back to DCF. In which case, what we're saying is that it will be in any case, it will be no worse than DCF, right? That's one way. The second way is that's where TBR come in. For each cell, you then put a TBR on top. Now, TBR would actually, throttle the DCF rate down. And TBR with fast together can achieve time-based fair access. Okay, clearly, I didn't invent a lot of things, but I built on previous work. I mean, so there are some cool stuff that I did. There are a lot of, other great people worked on it for several years, and, our work greatly benefits from them. I don't have time to go through everything, but, if you want to talk more about particular work, can certainly talk to me. I guess one cool thing is that I feel fortunate to be in the NMS group and at MIT is that I really get a chance to work with 3 professors and 3 grad students. Harry, John, and Franz, they are really cool guys. And Carl and Ellen and Eugene. And most of the time, sometimes, often they may not appear on papers, but, I certainly benefit a lot from discussing with them. So my interest, clearly, one is wireless networking. So another thing that we can do enhancement, which I can talk more about it later, is also separation. Because we solved the congestion control problem in the MAC layer without needing any feedback. Now, synchronous, you don't really have to be that the X has to be synchronous anymore. The ACK can, acknowledgement scheme could be SRP, selective repeat, use transmit at some other time. And you may be able to piggyback these information, especially data is in bidirection, which is what happens when you have TCP flow. So all kinds of, it basically creates other opportunities of optimization for other different schemes. And that's one thing that, in the future work we can do. And also work on a network management and security firm called Mazu, and I spent 3 months and worked on this clustering algorithm that was shipped as a product at the end, and they filed some patents and was good for me. I also got a publication on Usenix, so it was fun. Okay, so some people will ask, because I put security there, and it's not really a security algorithm, but it's more of network management and monitoring stuff. So, and then I got interested in game theory, and so I published a paper at Infocom on basically showing that how 802.11 as well as 802.11e in many cases could lead to inefficient and undesirable equilibriums, and what are the ways to solve that. And I worked at a small company called Echelon. They do embedded devices automation and stuff like that. And I had on C++ at the network layer, also at the applications layer for about 2 years. In conclusion, time-based paralleling fairness is desirable and achievable. And distributed scalability can also be achieved with FAST. And thanks for coming to the talk.
Any other questions?
Yeah, Alec.
I just have a high-level question. This seems to me a sort of something payoff.
Yeah.
Right? So you agree with that?
Yeah.
That's actually very cool. Because we obviously good problem at the same time. But you're still mostly focused on saturated case. For the unsaturated case where there's content-based advantages, this still preserve, right?
Yes, exactly. It's excellent. So it's really, sort of this combine the idea, in some sense, time-based fairness is basically, if you run TDMA and everybody use the same slots and you provide among equal slots, then that's sort of TDMA. The problem in TDMA is that it's centralized. And the thing is, you don't know when for data traffic, right, bursty traffic, you don't know when the clients have data to transmit. That's the reason why, one of the reasons why 802.11 uses distributed MAC protocol. But the problem with distributed MAC protocol is inefficient. As the number of node increases, you are less throughput, and it's unpredictable in a lot of ways. So in some way, we're trying to sort of combine a lot of the good things with the TDMA and CSMA and see whether we can find this approach where we got sustained throughput. So just like TDMA, no collision, we take a penalty, maybe 6-7% collision. And so basically, optimal is 100% throughput or utilization all the time. But we basically go down, okay, for distributed, we take 9% penalty or whatever, including the idle time and collision. But no more than that, right? So within 9% of the optimal, that's what we would achieve irrespective of load. And you got distributed. And you don't need to, have a centralized server. Yeah, thanks. You have a question? No? Okay, similar, right. Yes, I would, definitely. Yeah, definitely. And another thing about QoS, what this can facilitate QoS is that, so at the end, you really want to have an idea of what long-term time allocation for each node is going to be. Each flow is going to be, right? Each link is going to be. On top of that, each link, when I say it's a client AP pair, right? It could have multiple flows. One is an audio flow, one is TCP flow. So suddenly, FAST can facilitate, right? You can run another thing on top of FAST and say, okay, FAST can facilitate in such way so that audio flows set the CW in a very different manner than TCP flow. So FAST will allow audio flow to set a smaller CW and get to go real fast. So then you reduce latency. But then it's still keeping track of all the channel time usage and all the long-term usage, right? So now, for the same link, if there's a TCP flow cannot go fast. Now it needs to pay for that pay for that latency sensitive applications usage, right? It gets to access the channel faster. Now it probably will access at a longer interval. So there's suddenly this way to optimize it. So then at the end, what will happen is fast ensures that the amount of traffic going into the channel converges to long-term time allocation, and it ensures that you don't put more traffic than the channel can support, whereas you can still run QoS on top, and it would still work. And I haven't done a lot of experiments yet. That's also the next step. All right.
Okay.